Good morning, class. Get the fuck out! And don't come back. Right, let's start. Here are the top 8 most important electronic components and how they are used in everyday circuits. Okay then, let's start with the resistor. The name says it all, really. All a resistor does is resist the flow of electrons. But what does that actually mean? To get a better grip on this, let's compare it to a kitchen tap. The mechanics are remarkably similar. For this explanation, I am going to need a hand. Come here, Billy.
Okay.
I just need you to stand under the tap for me. The valve in a tap acts like a resistor in a circuit. When it is wound up, only some water can pass. But when it is unwound, water flows. We use resistors every time we want to regulate the amount of current in a certain part of a circuit. For example, we would want to use a resistor in a simple LED circuit to stop it from exploding. Okay, Kevin, you can come back in now. Shut up, Kevin. No one likes you. Right, time for capacitors. A capacitor is made from one insulating plate sandwiched between 2 conducting plates. When a voltage is applied across the capacitor, electrons jump from one side to another, charging the capacitor up. When fully charged, a capacitor can be used as a mini battery. A normal-size capacitor could not alone be used for charging a phone or power a computer. So what is this mini battery used for? It has 3 main use cases. Number 1, smoothing. They turn bumpy electricity from a wall outlet into smooth, steady power for your electronics. Number 2, energy bursts. If you need a quick energy burst, a capacitor is for you. They power camera flashes by storing up energy and releasing it all at once. Number 3, filtering. They can block direct current while letting alternating current pass through, which is vital for radio and audio equipment. Now let's learn about inductors. An inductor may just look like a simple coil of wire, but there is much more happening that you can't see. When passing an electrical current through an inductor, it generates a magnetic field. This magnetic field resists the rate of change of current, briefly slowing it down. Think of an inductor as the muscle of a circuit. It uses electricity to create a magnetic field that can push or pull physical objects, which is the secret behind how every electric motor spins. Diode time. A diode is essentially a high-tech one-way slide for electricity, just like the one monkey just came down, crafted by slapping together 2 layers of silicon, N-type, which is packed with extra electrons, and P-type, which is full of holes for those electrons to fall into. At the junction where they meet, they create a natural barrier that current can only cross if it's flowing in the right direction. This is called the depletion region. In forward bias, the electrons get pushed down the slide and flow freely. But in reverse bias, the barrier widens into a wall that makes it impossible for current to climb back up. This unique physics allows diodes to rectify power by stripping away the backward half of alternating current, AC, to create steady direct current, DC, and to protect sensitive components by acting as a safety valve that slams shut if a battery is plugged in backward, or if a motor tries to kick a dangerous voltage spike back into the system. Now we have completed half of the lesson. Anyone got any questions?
Does your head ever get cold?
At least my mama loves me! Transistor time now. A transistor is the ultimate upgrade to the diode, created by sandwiching 3 layers of semiconductor material together to form an NPN or PNP structure. While a diode is a simple one-way valve, the transistor acts as a controlled gate with 3 terminals: the emitter, the base, and the collector. In an NPN setup, electrons want to flow from the emitter to the collector, but they are blocked by the P-type base layer in the middle, which acts like a wall. However, when you inject a tiny amount of current into the base, it changes the chemical properties of that middle layer, effectively lowering the bridge and allowing a massive flood of electrons to rush through the entire component. By using a small electrical signal to manipulate a much larger one, the transistor can either act as an amplifier, making weak radio signals loud enough to hear, or as a binary switch, representing the ones and zeros that power every digital processor on the planet. Billy, get your ass up here. Billy, where has everyone else gone?
I don't know.
Go sit on that stall for me, and I'll be back in a sec. I'm back, Billy. Oh, where have you gone? Never mind, I will get him back later for making fun of my shiny head. I hope you understood how transistors work, because now it gets complicated. Now time to learn op-amps. Unlike a single transistor, an op-amp features two distinct inputs, inverting and non-inverting. Its primary job is to measure the voltage difference between them and multiply it by a massive gain factor. In its raw state, the tiniest nudge on one input slams the output to its maximum power limit, but the true genius of the component is unlocked through feedback. By looping a portion of the output back into the inverting input, you tame the circuit into a precision instrument that follows the golden rules. The op-amp will do whatever is necessary to make the voltages at its two input terminals equal, while drawing effectively zero current into those inputs. This forced stability allows the op-amp to perform essential tasks ranging from summing multiple audio signals and filtering out electrical noise to acting as a voltage follower or buffer, which gives a weak, fragile sensor signal the electrical muscle to drive a heavy load without losing a single millivolt of accuracy. Where the fuck has everyone gotten to? I guess let's go find them. Mr. Monkey, where are you? Billy! What the fuck are you guys doing? Stop watching that. Let's learn about real transformers. Hang on, where is Billy? Ugh, never mind. Get off there, Kevin. You're distracting the audience. That guy is so weird. Anyway, a transformer is the heavy lifting muscle of the electrical world and the absolute master of energy conversion. To build one, take two completely separate inductors, the primary input and the secondary output, and wrap them around a shared heavy iron core. The brilliant secret of the transformer is that electricity never actually flows directly from one side to the other. Instead, it relies on electromagnetic induction. When alternating current, AC, surges through the primary coil, it creates a massive, fluctuating magnetic field inside the iron. This invisible magnetic force reaches across the gap and physically induces a brand new electrical voltage in the secondary coil. By simply changing the ratio of wire wraps between the two sides, the transformer becomes a master of leverage. It can step up a power plant's output to hundreds of thousands of volts to blast energy across continents, or step down that lethal wall voltage into a gentle trickle safe enough to charge your phone, all while providing perfect electrical isolation to keep your delicate electronics safe. Wait, where am I? Billy, is that you?
Yes, it's me. Please come and help me.
What does that sound?
Oh, crap. How dare you come in here and try and take what's mine?
Honestly, you can have him. He insulted my shiny head earlier, so he deserves to stay here.
Oh, I'm sorry to hear. Billy, you have been a bad boy. I'm going to have to teach you a lesson tonight.
Okay, well, I cannot explain how it all works in detail, but I can give you a clear overview of what it does. If the transistor is a single light switch, the processor is a city of billions of those switches working in perfect sync. To tame this beast first, you must learn its rhythm, the fetch, decode, execute cycle. Every billionth of a second, the CPU fetches the instruction from memory, decodes it to figure out the math, and then uses its ALU, arithmetic logic unit, to execute the command. It's a high-speed calculator that treats everything, from your mouse clicks to high-end video games, as a series of simple additions and logical yes-no questions. To keep this chaos organized, a clock acts as a metronome, telling every single transistor exactly when to flip. Because reaching out to main memory is slow, the processor keeps a store of data called cache right on the chip. This allows it to stay at maximum speed, turning raw electricity into the digital logic that powers every screen on the planet.